Here we go into the final installment of the Chapter 20 lecture. So the last things that we have to cover are corrosion, electrolysis, and concentration cells. So just a few more topics. This video shouldn't be overly long, but we'll see. You know how I can talk sometimes. But focusing here on corrosion is our next topic. And essentially corrosion is just another type of spontaneous redox reaction. So the one that we often immediately comes to mind for most of us is the rusting of iron. So that's the corrosion of iron. Well, if we take a look, we also can recognize this one as a combustion reaction, right? Because it's something reacting with oxygen gas. But what we want to pay attention to in these terms is that the oxidation numbers here are 0 for the iron, 0 for the oxygen here, but the iron here is a 2+ and the oxygen is a 2-. So iron is being oxidized let's do a slightly heavier line weight there. Iron is oxidized from iron solid to iron 2+, and oxygen is reduced from oxygen gas to 2O2-. Right? So the question is, why does this happen? Okay? And hopefully your immediate thought is to think about the potentials. Okay? Why does oxygen get reduced, and why does it cause iron to be oxidized? So coming back to this idea that we had earlier, that the one with the more positive reduction potential is the one that will be reduced. Right? So if we go to our table and we take a look at, for example, table 20.1, we're going to find the half reactions for this scenario. And we'll see that we have one half reaction is the iron 2+ plus 2 electrons goes to iron solid. And the E0 there is plus 0.44 volts. Okay, our other half reaction is oxygen being reduced. So we're going to find the one that has O2 gas. And oxygen being reduced, its half reaction, the complete half reaction, looks like this. 2H2O plus 4 electrons goes to 2H2O, okay? Rather than 2O-. The way this half reaction works is that when it's balanced, it has its waters, okay? So more or less balanced. But anyways, it's E0, which is really our focus here, is plus 1.23 volts, okay? So more positive than the reduction potential for iron. So that means that oxygen gets reduced forcing iron to be oxidized. Okay? And because of the reduction potentials, this is a spontaneous thing. When you have two things put together and you look at their reduction potentials, the one that's more positive will take over and be the one that gets reduced. And this is spontaneous. Okay? So anytime you're wanting to know, will something corrode something else, you're looking for, is this going to be an oxidation? Can I oxidize iron with oxygen? And the answer is yes, because of the reduction potentials. And we looked at this at the end of the previous video when we were, maybe not the end of the previous video, but in the previous video, about deciding whether or not a metal could be oxidized by an acid. Well, this is the exact same idea, okay? The iron gets oxidized by the oxygen, and that causes corrosion. Okay? So how do we prevent this? Okay, there are ways to prevent this corrosion. How to prevent corrosion. Okay, and there are a couple of ways, the simplest of which is a thing called a sacrificial anode. Okay, so if iron is being oxidized by oxygen, that means that iron is the anode. But if I make a scenario where something else gets oxidized instead of iron, it becomes the anode and will corrode instead of the iron. So let's see how that plays out. So the way I'm going to do that is I'm going to physically connect a metal with a more positive reduction potential. Physically connect if I use something with a more positive reduction potential than iron, then it will be oxidized instead of the iron. So the way I'm going to do this is the metal will be physically connected. I just realized that I wrote the word connect twice, but will be physically connected to the iron via either just plated right on there, bolted right to the surface of the iron, or connected by a wire so that electrons can travel. All right, so let's sort of look at what we can use. Essentially, I want to find something higher up on the reduction table than iron, but lower than oxygen, so that oxygen still is the one being reduced, but I want to find something else that will be oxidized before iron will. So the oxygen's reduction potential was plus 1.23 volts. Okay, and if I go down the table just a little ways, I'm going to find a likely candidate in zinc. Okay, so zinc solid can be oxidized to zinc 2 plus 2 electrons. I just realized my Z's and my 2's look very, very similar. Hopefully you're keeping track. The E0 for that reaction, for the reduction potential for that reaction is plus 0.76 volts. And then let's take another look at what happens with the iron where it sits. Its E0 was plus 0.44 volts. Okay, so electrons, you can think of electrons kind of traveling down the table. Okay, so if oxygen is going to be the one reduced, the next closest thing down on the table is the thing that will be oxidized. Zinc will be oxidized before iron will. Okay, so zinc gets oxidized instead of the iron, so to speak. Okay, so let's take a look at how we can sort of think about this in real life. So let's imagine Dr. Lyon can draw. I know it's kind of crazy. Well, let's imagine that we have a flagpole. Okay, and it's made of steel, which is primarily iron. Okay, let's just say it's an iron flagpole. Now, it would be really unfortunate if anything made of iron just rusted away over time. It would essentially have prevented mankind from leaving the Bronze Age back in history. But when they started to figure out how to blend their metals, we figured out how to start protecting metals. All right, so over here we have a zinc. We're going to call this a zinc slug, just a chunk of zinc. And it's buried in the ground. Okay, and the zinc slug is our sacrificial anode. Okay, and the way that I prevent my iron from being oxidized, I want the zinc to be oxidized instead, is I'm going to connect these by a wire. Okay, some sort of conducting wire. Right, so what happens is when the zinc gets oxidized, the electrons will travel up the wire toward the flagpole. Okay? They travel up the flagpole to the iron flagpole. And what it does is if iron is gaining electrons, by that action, it keeps the iron reduced. So we get no corrosion. Of the iron. Okay, and this happens on things like ships' hulls. Imagine if you had like these giant freighter ships that cross the oceans all the time, and their hulls are made of steel, which is primarily iron. And imagine what would happen with all that salt water just being in contact with plain old steel. That iron would rust in a heartbeat, and there would be no way that those ships could cross the ocean. But what they do is they stick a giant chunk of magnesium plating on the surface of the ship. And the magnesium serves as a sacrificial anode. The magnesium rusts away instead of the iron of the ship. Okay? So our next topic is concentration cells. Okay? So talking about concentration cells, the point of a concentration cell is, or let me back up. The reason that we're getting into concentration cells is that we want to talk about different types of electrochemical cells. So we focused so far only on galvanic cells, okay? Things that have different species and will run spontaneously. But a concentration cell is a little different in that it's simply a cell under non-standard conditions. Okay? So whenever you have a cell under non-standard conditions, you need to be thinking Nernst equation. Okay, so remembering standard conditions, everything's 1 molar. But if things are not 1 molar, we need to be thinking about using the Nernst equation in order to figure out what kind of cell potentials we're going to get. Now, the other aspect of concentration cells that makes them unique is that you have the same components on both sides. Okay, so far we've been talking about galvanic cells that have, for example, copper in copper ions on one side and zinc in zinc ions on the other side, 2 different things on each in each half reaction. But with concentration cells, we have the same components on both sides, but different concentrations. This is why we call it a concentration cell. Okay. So we're going to be thinking about using the Nernst equation. So let's put that up here, remind you how that looks. So E equals E0 cell minus 0.0592 volts over N log of Q, assuming that we're doing things at 25 degrees C. So let's take a look at what a concentration cell sort of looks like. And this is the one from the textbook. Notice that we have nickel on both sides, but different concentrations of nickel on each side. We have nickel anode and nickel cathode. So what's going to happen is while we have different concentrations, electrons will flow from the low concentration side to the high concentration side. Okay? And they'll do so until things end up at the same concentrations. Okay? Once they reach the same concentrations, notice there is no more voltage, right? But while we're at different concentrations, we do have a measurable voltage. Okay? So why does this work? Okay? So on the anode side, the anode is nickel, and it has an E0 of plus 0.28 volts. Okay? The cathode side is also nickel, which means that it also has an E0 of, how I can start writing a plus or an equal sign and end up with a circle, I don't know. Come on. All right, so if I calculate E cell normally, which is totally cool to do, I'm going to have plus 0.28 volts minus plus 0.28 volts equals 0. Okay, so when I go to utilize my Nernst equation, E0 cell has a value of 0 because I have the same components on both sides. Under standard conditions, everything 1 molar, I should have no voltage. Okay, so let's take a look at what else we need to be thinking about here and why electrons flow in the direction that they do. So at the anode, the anode is going to have an oxidation happening. So if I write out an equation for that, I'm going to have nickel solid, showing the oxidation here, to nickel 2 plus aqueous, dilute, plus 2 electrons. Okay, notice this is a 2 electron process. Okay. And on the cathode side, I'm going to have the reduction. So I'll have the nickel 2 plus, concentrated, plus 2 electrons going to nickel solid. Okay, so if I combine those two reactions and show the overall reaction, my electrons cancel out, my nickel solids cancel out. I'm going to have my nickel 2 plus aqueous concentrated going to the nickel 2 plus aqueous for the dilute side. Okay, so let's write a Q expression, okay, because that's the next piece that I need for my Nernst equation. So given this information, Q, products over reactants, so Q will have nickel 2 plus dilute over nickel 2 plus concentrated. Okay. So let's calculate E cell for our concentration cell. So E equals 0. That's our E0 cell that we calculated before. Because we have the same species on both sides, E0 cell will come out to be 0. So 0 minus 0.0592 volts over 2 electron process log of the dilute over the concentrated. All right, so let's go ahead and plug in some numbers here. And my concentration of the dilute was to the minus 3 molar, and my concentrated side was 1 molar. Right? When we do that arithmetic, we end up with an E equals plus 0. Okay, so, and then remember, the cell will continue to run until the concentrations end up the same on both sides. Okay, so as the oxidation side does its thing, the nickel solid becomes nickel 2 plus. So as the cell runs, my concentration, actually let's come back to our image. So as my cell runs, my nickel solid comes off into solution as nickel 2 plus. So as it does its thing, we get more nickel 2 plus on the left at the anode side. On the cathode side, the nickel solid is becoming, the other side, the nickel 2 plus is becoming nickel solid. So my nickel cathode will gain in mass, my nickel anode will lose mass, but eventually my concentration of ion solution on both sides will equilibrate. Right? So concentration cells sound complicated. They're really not. All they are cells that have an E0 of 0, and then log of Q is just dilute over concentrated. Our last topic in this chapter is electrolysis. Okay, and our first thing that we want to look at in the topic of electrolysis is a electrochemical cell, an electrolytic cell that runs in molten salt. Okay, but let's back up a little bit and sort of talk about what electrolysis means. So electrolysis essentially is just forcing the non-spontaneous reaction. And we do that by applying an external voltage. Okay, so your spontaneous reaction will run without any help, but you can force the reverse reaction by applying some sort of external power source. Okay, and this is an example of this is rechargeable batteries. So a fully charged battery is an spontaneous electrochemical process waiting to happen. So as soon as you connect the two ends of the poles with some sort of circuit, then your spontaneous electrochemical reaction will just run. But in order to recharge the battery, what do? You plug it into a power source. That power source causes the reverse reaction. So you rebuild your anode, you deplete your cathode, so that when you are ready, that system is ready to go again. Okay. So, but talking about the cell that we've got here, okay, is a electrolytic cell. Notice that it has a voltage source, okay, an external voltage source that's going to cause the non-spontaneous reaction to go. All right, and it's done in a molten salt, okay, and molten salt electrochemistry is really, really fascinating and very, very useful because there are a lot of reactions that are desirable that you can't do with water, okay? Because what happens is with water, you will have, before your electrochemical process happens that you want to happen, water or oxygen or something will be reduced or oxidized in its way, and you won't be able to take care of the reaction that you want, okay? So what happens is if we do this in a molten salt, so quite literally they take a quantity of solid sodium chloride and they heat it up to better than 800 degrees C, okay, because ionic salts have very high melting points, but they literally melt the salt, so that's why it's called molten salt. And so everything of this type of reaction takes place at very high temperatures. Okay, so let's talk about why we want to do this. Okay, so normally, under normal conditions, okay, we look and in this example we would have chlorine gas plus 2 electrons. Look up the reduction equation, the reduction half reaction for chlorine, and we would get something that looks like this, and it has an E0 of plus 1.36 volts, right? And we look up the reduction potential and the half reaction for sodium, and we're going to find and it has an E0 way down on the table, minus 2.7 volts. Okay, so looking at those reduction potentials under normal conditions, the spontaneous reaction hopefully you would notice immediately that chlorine has the much more positive reduction potential, so it's going to be the one reduced. So spontaneously, chlorine gas is reduced, and sodium solid is oxidized. Okay, so chlorine gas gets reduced to chlorine minus, and sodium is oxidized to Na plus. Okay, but what if I want to make some solid sodium? Okay, so if the spontaneous reaction is to make sodium ions, apply external voltage, and what I get is making sodium plus, or excuse me, sodium solid. Okay, so applying the external voltage would cause this to go the other way. So applying the external voltage, now I would have sodium ions reduced to solid sodium, and I would have chlorine ions oxidized to chlorine gas. Okay, so in this way, I can take a reaction that normally wants to keep those ions separate and in their ionic states, and I can create useful materials. Okay, so if I wanted to make some solid sodium and some chlorine gas, I could do it using a molten salt electrolysis cell. Okay, and we're going to, in these cells, we're going to use inert metal electrodes. Okay, so I don't want anything to participate in my reaction. Just give it a surface. Okay, so let's come back up to our image here. So what's going to happen is that on my cathode electrode, okay, and the electrodes will be something inert, sort of. I could use platinum as a really common one, because platinum is very, very hard to get to participate in any kind of electrochemical reaction. And I would have it on both sides. Both electrodes would be platinum, or some other type of inert metal that's not going to participate. So over here, I've got sodium ions coming out of the solution. So I would end up with some sodium liquid, because we're still at very, very high temperature. So it would be liquid sodium. But if I cooled it down, I could get some solid. I could get solid sodium. And then over here on the surface of this one, I'm going to get my chlorine gas bubbling up. And I could devise a method for collecting that chlorine gas. Okay, so for our last thing, we're going to look at electroplating. Okay, and electroplating is another kind of electrolysis, okay, where I'm going to apply an external voltage source, and I'm going to cause something to be coated in the metal of something else. Okay, so let's look at this particular electroplating cell. Okay, and this is another type of electrolysis, so applying some sort of external voltage to cause a non-spontaneous reaction to happen. So what's different about electroplating as opposed to our electrolysis cell in molten salt is that here I have electrodes that are going to participate in the reaction. Okay, so instead of inert metals, I have metals that will participate. Right? So we have, in this scenario, we have everything taking place in an aqueous copper sulfate solution. Okay? That means water is present. Right? So if I want to decide how things are going to go, all right, let's look at the reduction potentials of copper 2+, aqueous, and water. Okay. All right, so our E0 for the copper is minus 0.83 volts. My E0 for water, oh, excuse me, that's the one for the water. My copper is plus 3.4 volts. 0.34 volts. My E0 for the water reduction is, gosh darn it, 0.83 volts. Okay, so between the two, the copper is preferentially reduced. Okay, so what it does is that causes, let's come down here, if the copper ions are preferentially reduced, it causes the copper metal to be oxidized. Okay, so my 2+ is reduced, and my metal is oxidized. Okay, so my solid metal is coming off and becoming copper ions. And then because I have another metal electrode in there, that serves as my cathode surface. So my copper ions collect on the surface of the metal as copper solid. Okay? And so in this way I can coat that surface with another metal. So nickel plating, chrome plating, copper plating, all of those things take place by this process. And on a side note, if you ever happen to find yourself up in Moline, Illinois, that is the home of the main John Deere factory for the entire world. One of the biggest factories in the John Deere Corporation, and they have their main electroplating facility. So if you ever find this interesting and you find yourself up there, you can actually go and take a tour of that electroplating facility, and you'll see large vats of concentrated acid, and you'll get to see how they coat every single piston of every single tractor that John Deere makes with a nickel chrome plating to prevent corrosion. So this is another way that you can prevent corrosion, is by plating a metal with another metal. So I hope this was interesting for you. I hope